And number 5, they want to know, why does an ion of phosphorus have a larger radius than a neutral atom? And so I've drawn a Bohr model of a neutral phosphorus and then a P-3 down here. So if we're going to explain these, and clearly they're talking about attractions and repulsions and that kind of thing, it's always a good idea to make sure that you know how many particles there are. And you notice that phosphorus has 15 protons, and that is not going to change in the ion. And there are 3 shells, 1, 2, 3. And so I've drawn 3 shells of electrons, but I'm not going to actually draw the electrons in. The real difference would be that, of course, on the outside, there's 1, 2, 3, 4, 5 electrons in P, and there's 1, 2, 3, 4, 5, 6, 7, 8, because it fills the shell to get to P-3. And so if we're thinking about the difference, recognizing that difference in number of particles will be important. Let's look at the answer choices. There's a greater Coulombic attraction between the nucleus and the electrons in P-3. And that can't be true because there's the same number of protons in both of them, and the distance to the outer shell is roughly the same. So I don't think that's likely. And then B, the core electrons in P-3 exert a weaker shielding force than those of the neutral atoms. And that can't be true either because there's 2 shells that are completely full as core shells in both of them, so they have the same amount of shielding. C, the nuclear charge is weaker in P3- than it is in P. That's not true either. They both have 15 protons. So the answer must be D. Let's see what it is. The electrons in P3- have a greater Coulombic repulsion than those in the neutral atom. And that's true because they repel each other. There are more electrons in P-3, and so there's going to be more electron-electron repulsions. Alright, number 6. So I've looked at this one and I'm pretty sure that they have an error in it, but we're going to do it anyway because it's instructive on how you do empirical formulas without a calculator. Usually they're set up quite a bit easier than this one, and as far as I can tell, there doesn't seem to be any absolute correct answer here based on the fact that 16.5% of it is copper by mass. So let's look at it, the traditional way we'd solve it and maybe potentially a different way we could solve it. So we know that copper is 16.5% by mass, and we're going to convert that to grams because we're going to assume it's a 100-gram sample. And you remember traditionally we changed grams to moles by dividing by the molar mass, which is 63.55. And when we did that, we could get the gram amount. And so we do the same thing, or the mole amount. Then we do the same thing with iodine. And iodine, you remember that if the whole thing is made up of 100% and 16.5% of it is copper, then the amount of iodine has to be the remainder, which would be 83.5%. So we're going to assume that that's grams, and then we're going to convert the grams to moles. And the molar mass is 126.91 grams. And so there we go. We have the 2 of these, and we can figure them out. Now, normally we'd get out our calculator and figure it out, and I am going to do that exactly in a minute. We're going to put the exact calculated amount in these boxes to check and see if I'm right, that there's no exact correct answer. But let's try to approximate it. So 16.5 divided by 63, let's think about it this way. 16 divided by 32, 32 is twice that, so the answer would be 0.5 if it was 32 on bottom. So 32 twice that is 64, and so that's pretty darn close to 63. So I think 16 is about a quarter, or 0.25 moles. So we're just approximating really. In a minute we'll do the exact number. Down here, 83 divided by 126. Well, I know it's not 0.5 because 83 divided by like 160 something would be 0.5. So it's not quite that much of a cut. So it looks to me like it's somewhere between 0.6 and maybe 0.7. And then we could approximate it out. And we're going to do that in just a minute. But let me get the exact values in here. Alright, so here are the exact values. According to the calculator, it's 0.26 for copper and 0.65 for iodine. Now, of course, we don't have a calculator, and so we would normally have to take, you remember at this point, we're going to set the copper equal to 1 by dividing both sides by 0.25. So copper will turn out to be 1, and iodine is going to be something like 0.6 to 0.7, although now we know it's really 0.65, divided by 0.25. So this value is going to be, well, it's going to be more than 2 and not quite 3. So by our estimation, we're coming out somewhere between B and C as our answers. Let's see what the actual calculator says when I do it by the calculator. Alright, and so if I use these two values, I do 0.65 divided by 2.6, I get Cu as 1 and iodine as 2.5. So it did come out in between B and C, which tells you that there's something wrong in this particular review book. If we actually got this, we'd typically say, well, you know what, our answer is really going to be Cu2I5, but that's not an answer choice. So clearly there's a mistake in this one, but thinking about this strategy is as a way of dealing with how to deal with these problems is a good one anyway. So in summary, no correct answer. If you guys find that I'm wrong somehow, let me know, but I don't see a correct answer in this one. This one, they want to know which neutral atom would have the most unpaired electrons, as in is the most paramagnetic. And so let's look at it. Titanium is right here. Titanium has its highest energy orbital is, let's see, 1, 2, 3, 4. It's in the fourth row, so its highest energy orbital is 3d2. Which you remember, it's good to imagine what those look like. There are 5 lines and there's 2 electrons. So I think titanium has 2 unpaired electrons. We do the same thing with manganese. Manganese is 3d 1, 2, 3, 4, 5. And so it looks like it's going to have 5 unpaired electrons. So that definitely is the best so far. Nickel is right here, and it has 8. And you notice what they're getting at is since nickel is 3d8, it's not like there are 8 unpaired electrons, because when we actually draw them into the 5 orbitals, 5, 6, 7, 8, it leaves you with only 2 unpaired electrons. And then lastly, zinc. I think we're going to find zinc is 3d10, which means all of the orbitals are filled, so that's not it either. B must be the correct answer. Alright, and then 8, which element will have a higher electronegativity value? Remember, electronegativity is the pull on electrons in a bond. Some helpful things to orient you is that fluorine has the highest electronegativity of any atom on the periodic table. So as you go up and as you go right, things become more electronegative. So since we're comparing chlorine and bromine, clearly chlorine is more up, and so it has higher electronegativity. So that kind of answers the question pretty quickly. We can get rid of B and D. And now we're just coming down to the reason. So chlorine because it has less Coulombic repulsions amongst its electrons, or chlorine because it is smaller. So the answer turns out to be C, chlorine because it's smaller. And I got to tell you, I don't particularly like that answer. I mean, it's true, right? And chlorine has 1, 2, 3 shells. And so the nucleus has a much stronger pull on the electrons than it does in bromine, which has 4 shells. So it's definitely true. Let's look at A. Chlorine because it has a less Coulombic repulsion amongst its electrons. And that seems somewhat true too. In other words, there are more electrons but in the core shells here of bromine, but I think the distance is probably the greater impact here. So it's kind of a tough one. I'm not sure about that one.